Well, welcome back. We're going to begin another lesson. This one is lesson 10, and we're going to sort of take a step back really to the beginning. We're going to talk a little more about how do we process these metals. We've spent a lot of time in the course up till now really talking about structure and properties. And we've sort of let that processing realm sort of sit in the background and just assume that that's how these structures and these properties just almost appear. But there's a lot that goes into the processing of metals. It's really more of an area where I tend to spend more of my time thinking about. And what we're going to do in this lesson is go over several of the major areas that consist of processing. We're going to start with what we call thermomechanical processing, which is for the most part having a finished ingot or some type of very simple product form, and for the most part heating it and beating it into shape, very much like a blacksmith. And we'll talk about casting and solidification, and we'll move into welding and joining, and an area that I'm heavily invested in because of my interest in work in additive manufacturing is in the area of powder metallurgy. So we're going to talk a little bit about that as we move forward, but let's jump into what we have for the lesson now. We're going to start with Sir Isaac Newton, and I think what it sort of talks about is what we're going to see here is these appear to be sort of older processes, ones that you might think it's fairly dated, everybody knows how to do it, but there's so much little bit of science that was passed down, and we still spend a lot of time even as scientists today of looking at these what may be considered rather simple processing techniques and really still trying to understand them. And so in this lecture, we're going to talk about those forming operations, or what I like to call these thermomechanical. There's a thermal component and there's a mechanical component to it. Very much we'll see how that goes. And so in the videos that we're going to show is there's going to be a lot of pressing. There's a lot of large pieces of equipment that work to produce these different types of product forms that you're going to work in. And we'll start with the basis for hot and cold rolling, get into some forging operations, and then hydroforming is a little more modern version of some of the closed die forging that we may look at. And then an important distinction that you're going to see is the difference between extrusion and drawing. One pushes the material through a die, the other one pulls it through a die, and there's some very specific and different applications that they both work in. And so we start to see here with our terminology, we're going to see the difference between hot and cold working and what that actually really means. It's pretty self-explanatory if you sit about it. If you're going to work something or deform it, you're going to deform it at high temperatures, it's hot working. At lower temperatures, it's cold working. And we're going to see why we do each of those through to how we do forging and these other processes. So brings us into how are metals fabricated. We're not going to get into sort of the refining, the alloying, and in some cases the heat treating. There are certain what we consider processes that give us a general shape. And so we can either do that by deforming the material, whether it's hot or cold, and that's where these forming operations are. And you look at it, forging, rolling, extrusion, drawing tend to fall right in this. This is what we're going to talk about in this lecture. Casting is another one, where that takes you directly from a molten metal to a product form of some type. And then powder metallurgy and welding. A lot of people look at additive manufacturing as this fourth generation of the fourth industrial revolution and some different things like that. And I will have an extra credit opportunity later discussing some of that. But for the most part, a lot of the processes that we see in additive manufacturing are some combination of what we already know about powder metallurgy and welding. So if you have a background in these two, additive manufacturing makes a lot more sense as we move forward. So we can fabricate these shapes. In most cases, you look at these, we're mostly looking at getting to a shape. But outside of that shape, there's certain properties that we're really trying to get out of that metal, and that depends on how we're going to process it. And the big one of all is cost. We can never escape the accountants telling us what to do. If your other professors haven't told you, you're going to be answering to accountants for your entire career, so you might as well get started on that, understanding that now. But cost is going to drive the selections you make, but properties are always underlying. It doesn't matter if a casting is cheaper and it doesn't meet the properties for an application, you're still not going to use casting. You need to stand up to the accountants and tell them that can't be done. Is that it needs to be either forged or rolled to give you the properties you need. So these forming operations give us the shape, but we change it by plastic deformation. If we remember from earlier on in the course, when you plastically deform something, it actually gets stronger, even though it's above the yield strength. You're sort of damaging it, but we're taking advantage of those defects. Now, the temperature at which we do it is really one of the big things. And the primary measure of that deformation is whether the temperature that we do it above is one where recrystallization occurs. Remember, recrystallization from the heat treating of cold work materials. If you take a highly cold worked material and you heat it up, it goes through recovery recrystallization, which is the appearance of fine strain-free grains, followed by grain growth. So if you go above the recrystallization temperature, it will tend to want to recrystallize on cooling once it reaches that temperature. But if it's above that temperature, it's much easier to deform because higher temperatures give us lower yield strength. If we're below that recrystallization temperature, sometimes the material strengthens too much, and so we can't deform it as much. And this is where hot working and cold working goes. And I provided a little bit of a list between the two. And so, we go back to these forming operations. The general look at a forming operation is the difference between this hot working and cold working. Hot working are done at these temperatures that tend to be above that recrystallization temperature, but large deformations become possible, and they can be repeated because the metal is still soft and ductile because it's so hot that the dislocations don't build up. The dislocations are going through recovery at the same time almost that they're being formed. So they're disappearing. And so the deformation energy requirements are lower, so you can use smaller presses if you operate at higher temperatures and be able to take that into account. The one issue, though, is that the higher temperatures do provide some surface oxidation, so you need to be careful. And we're going to see how they get around that in a couple of the videos coming up. Cold working, though, we're below that recrystallization temperature, so when we deform a material, we tend to increase its strength by adding all these dislocations. So we see a decrease in ductility. So there's strain hardening there. So the large deformations that were possible in hot working are not possible in cold working. But we do have better quality surface finish, we have better mechanical properties, and we can control that dimensional tolerance that much better. So of these hot working and cold working operations, one of the most widely used is just rolling. It's a rolling mill. We make plate. If you go look at how a lot of structures are made, you have what may be plate or long products that go into making them. And for the most part, to make plate, you pass a metal through two rolls, and it reduces the thickness. That can be done both in a hot working or cold working type environment. Hot rolling typically is in more of a primary metal, so you start with a very thick slab, and what we'll see in the hot rolling operation here is you start with about almost a 9-inch thick slab, and it's rolled down in a single step through a hot rolling operation to a thickness in the probably less than a millimeter or tens of thousandths of an inch. Cold rolling tends to be done after. So you do hot rolling first to get the deformation. You get that big plate or that ingot down to a reasonable size that you can work with it. Cold rolling is more finishing. You're trying to produce good surface finish, dimensional tolerance. So think about your automobile or your car. It's primarily made from sheet steel. That sheet steel had started off as a large plate. It was hot worked and then cold worked down. So anything you see on your cars has gone through a significant cold rolling and some type of plating operation. But you can also take these and you could specialize, produce different bars and shapes. An I-beam is a great example of a rolled type of product. There are other ones that we'll see here as we look through the videos here, but these are two that came from a European steel company called Chorus. They're both very good. So let's look at what they tell us about hot rolling of steels first.
Steel is highly resistant to shaping when it's cold, and for that reason, it is generally rolled whilst it's hot. To make sure the steel is at the correct temperature for rolling, it is fed into a furnace. Here it travels through several temperature control zones until it's at the correct temperature and ready for rolling. Whatever the product, the principles of hot rolling are the same. Steel is squeezed between rolls until the final thickness and shape are achieved. To do this, the rolls must exert forces of tens of millions of newtons, equivalent to a weight of thousands of tons. The rolls, therefore, run in massive bearings, mounted in housings of enormous strength and driven by powerful electric motors. These are known as mill stands. The layout of a rolling mill can vary from a simple single-stand mill to several stands positioned either side by side or in a line. The mill rolls themselves can either be plain for flat products such as strip, used for products such as cladding, or profiled for sections, beams and columns for use in construction. Mill stands have various roll arrangements depending on the product being rolled. The simplest arrangement is a two-high stand, used mainly for long products such as sections. For light sections and bars, three-high stands are sometimes used, with the steel passing one way through the bottom gap and back through the top gap. Four-high stands have two work rolls in contact with the steel, supported by larger backup rolls to prevent distortion caused by the rolling face. These give greater accuracy for rolling flat products, such as plate. Universal beam mills include stands with both horizontal and vertical rolls bearing on the steel simultaneously. Rolling processes are computer controlled and monitored up to 50 times per second. Despite the huge scale of some mills, accuracy to plus or minus 50 microns can be measured. The rolled steel is then cooled in a way appropriate to its end use and prepared for further processing or dispatch.
So we move into cold rolling at this point. We're going to see is really sort of a difference in scale, especially of the thickness of the sheet.
One of the further processes is cold rolling of strip. This is used to produce a thinner, flatter product than is possible on a hot mill, down to a thickness of 0.15 millimeters. Forming properties and surface finish of cold rolled strip is better. It can also be coated with zinc to protect it from corrosion, with tin for cans, and with a plastic coating or paint for protection and decorative purposes.
So we saw a little less going on with the cold rolling, but let's go back to what happens to the microstructure. So during hot working, we have these high temperatures, and so we have a given grain structure, and so we've had some grain growth, and what you can end up with is really elongated grains, and then if you control the temperature properly, afterwards you start to see some of this recrystallization. So you get a plate after it's gone through that's still very strong and has a much different microstructure or finer microstructure than when it started out as a large component. Cold rolling, though, it tends to be, we're working at lower temperatures. What we start to see is this loss of elongation as we start increasing yield and tensile strengths with that. So essential features of each: temperature for hot rolling is greater than the recrystallization. So at these high temperatures, you have a low yield strength material that's soft and ductile. So there's that lower energy requirement. So I don't need as big of a mill or a press of any type to be able to obtain that same level of deformation. But large deformations are typical, and these would be no reason to heat it up because it is costly to run it through the furnace and heat up some of these large components to the temperatures we start to think about. But it's this recrystallization temperature that we want to concentrate on. In cold working, we're lower than the recrystallization temperature. So now we start getting strain hardening. We have higher strength, lower ductility, there tends to be a higher energy. We have to use a bigger press, so there's a higher energy requirement, and then good surface finish between the two. So that tells us the difference between sort of hot working and cold rolling.